Hi everybody and welcome to a new video in the Pytorch for audio and music processing series. Last time we extracted MEL spectrograms using torchaudio. This time we're going to be working on something important, which is basically adjusting the length of our audio signals or waveforms before we make transformations. So why do we need to do this? Well, it turns out that when you deal with real-world dataset, audio dataset, like for example the UrbanSoundDataset that we are using in this series, you have data samples that have different durations or different number of samples. The problem is that with most deep learning architectures, what you want to have is data or training data that is fixed in its shape. And in order to ensure that we have fixed shape training data, what we need to do is ensure that the signal that we load before we process it and extract, for example, a MEL spectrogram is consistent, is fixed. It is all the same for all the different audio files that we are analyzing. So that's what we want to do today. So for doing that, we are going to do first one thing, which is basically deciding the number of samples that we want to have and a process. And so I'm going to add a new constant down here in the script called num samples, and I'm going to set this to 22,050. Now I'm also going to change the sample rate from 16k. I'm going to go to 22,050. Now, given that we are using the same number of samples as the value for the sample rate, what this basically means is that we are getting 1 second worth of audio. Cool. So now we have the expected number of samples, and we're going to pass it in here in the UrbanSoundDataset constructor. So this is going to be yet another argument for our constructor. Okay, so I'm just going to reformat this to make it nicer. And so num samples. Of course, now we have to jump in the UrbanSoundDataset class and here in the constructor and change it accordingly to what we've done just now. So I'm going to call this num samples. Now the next step is that of assigning num samples to an attribute called number of samples. Here we go. That. Okay, so now we have this extra attribute that is going to be handy for the work that we'll be doing. Now let's jump on and modify the getItemMagic method so that we can cut or pad the signal depending on whether we have more or less samples than the expected ones. Okay, so let's take a quick look at this. So let's start with the signal. So we load the signal, then we resample if that's necessary, we mix it down to mono, and then after that we pass it through our transformation, which in our example is a MEL spectrogram, as we saw in the previous video. Okay, but before we get to the transformation, what we want to ensure is that the signal has the number of samples that's equal to self.num samples. Okay, so we should, we may find ourselves into 3 different cases. So if we are super lucky, this signal has exactly the number of samples that we expect. And so that's fine. We don't have to do anything else. But there's another situation, which is where you have in your audio file less samples than the one that you actually need. And if that's the case, what you want to do is zero padding and actually write padding. So let's write this right now. So we'll do a self.write pad. I'm creating a new private method that we'll implement later on. So write pad if necessary, and I'll pass in the signal. So we pass in the signal, and if we are in a situation where we have to actually write pad, in other words, we have the number of samples of the signal that's less than those expected, then we apply write padding and we return the signal. Another option that we have is that a situation where we have in our signal more samples than the one expected. If that's the case, what we're going to do is just truncate or cut the signal and just leave the initial samples up to the expected number of samples. So let me write a new expression here, which is going to use another private method, which is cut if necessary. Okay, and I'll pass in the signal. Cool. Okay, so of course, these are a couple of new private methods that we still have to define. So let's define the first one. So cut if necessary. Here, this method takes signal as an argument. First of all, we should enter the conditional, right? And the conditional is, as I said, if the signal has more samples than the one that we expect, then we actually do cut the signal. But before we get like into the implementation, let's review real quick this signal that we pass in here. So this is a Pytorch tensor, which has a couple of dimensions. So the dimension number 1 is the number of channels, and we already know that this is equal to 1 because if it wasn't, we just like mixed it down here with this method. And then the second dimension is equal to the number of samples. So this could be equal to 10,000, 50,000, whatever that is, right? Okay, so now what we want to ascertain is that the number of samples, so this one here, this value here, is greater than the number of samples. So we have more number of samples proper to the signal than the expected number of samples, right? Okay, so how do we get like this value? Well, this is quite easy, really. So we can do a if, and here we'll say signal dot shape, and we take index 1. So the shape of the signal of this tensor is this tuple here, and then we take like the first index that it's actually the number of samples. Okay, so if this is greater than self.num samples, then we act and we actually cut the signal. So we take this signal and we use slicing. So we can use slicing just like we use it with numpy arrays, also in this case of Pytorch tensors. So in this case, it's multi-dimensional slicing. So for the first dimension, we use a column like this. And what this means basically is that we just like take the whole first dimension and we leave it completely untouched. But for the second, we do something else. So we leave untouched the first part up to self.num samples. So what this means is that we are basically getting, so let me give you an example because it's going to be easier. So here, let's say that we have 1 and I don't know, like let's say 50,000. Okay. Now we said that we expect 22,050 samples. So if we pass this one in this slicing, so what's going to happen is that we are going to, so this new signal here is going to have this shape, 22,050 samples like that. And these are going to be the first 22,050 samples. The rest, what comes after that, is going to be just truncated. Okay, great. So let's return this. Now, let me just remove that comment. Just a real quick consideration about what we built here. So if the signal doesn't satisfy this condition, then it means that we are fine, and then we just return the signal back without any modification to the signal itself. But if indeed we have the signal has more samples than the expected samples, then yes, we modify the signal through this multidimensional slicing and we return it modified. Great. So next step is implementing this write part if necessary method. Okay, so let's implement it here. Once again, we get a signal as an argument. Okay, so here we're going to need to get the length of the signal. Okay, and that's because we're going to be using like this value multiple times, so we can just save it, store it in a variable. So the length of the signal, of course, is this one here, right? So we just did it earlier for the other method. Okay, so now we have the length of the signal. What we the conditional that we want to check for is going to be satisfied if the length of the signal is less than self.num samples. So in other words, in case the number of samples that we have in the signal is less than the expected number of samples, we should apply right padding. Okay, so now let's define what right padding is. Okay, so I'll give you a super simple example. So here, let's say we have a list or an array, and this is 1, 1, 1. Okay, so let's say that I want to right pad this. So what I'll do here is I'll just copy this, and then let's say we want to right pad it with a couple of elements, and these items will be 0, so we are 0 padding. So we'll just add a couple of zeros here, and we are right padding because here you have the array, and we are just appending new items on the right of these things. If we were to left pad, we would actually prepend these values here. Okay, so now what we want to do is append new values on the right of the array of our signal. So that's right padding. Okay, but first of all, we should decide how many items we want to append here. And this is quite easy to calculate because the number of missing samples, right, is equal to the self.num samples. So these are the expected number of samples minus the length of the signal, right? So these are the number of missing samples that we want to append in order to arrive to the expected number of samples. Okay, so how do we actually apply padding? Well, Torch has a function that does that for us quite cheaply, quite easily. Okay, so here I'll put signal, and then here I should call torch.nn.functional. And here there's a function that's called pad. So pad takes the signal, the array that we want to pad, and then the a padding tuple. So we'll see what that is in a second, but let me just like put a variable like as a placeholder there. So last dimension padding. So now what's this last dimension padding? Okay, so that's something that we're going to build now. So last dimension padding. And so that is equal to 0 and number of missing samples. Okay, so now let's analyze what this is. Okay, so, and I'll give you an example here. So let's assume we have this array. Once again, let's do 1, 1, 1, so this tensor. Okay, so now let's say we were to apply last dimension padding, which was actually equal to 0, 0, 2. In this case, we would get 1, 1, 1, 0, 0, right? If we were to do a 1, 2, in this case, we would get a 0 prepended here, one item, and then all, the original array plus the 2 items on the right. So you get the point. So this is like the number of items that we want to prepend, so left pad, and this is the number of items that we want to append or right padding. Why did I use this last dimension padding name for this variable? Well, there's a convention with this pad function which says that each axis gets a couple of values that you can use to specify the left and right padding. So let me explain what I mean. So let's assume this was equal to 1, 2, or let's say 1, 1, and then 2, 2. So this was like our padding. Okay, so this initial two values would be the left and a right padding that we would apply to the last dimension of our tensor, whereas this 2, 2 are the values for the left padding and the right padding for the second to last dimension of our tensor. Okay, so in our case, we are only interested in kind of like adding padding to the last dimension. So let's remember like the shape of our tensor. So it's 1 because we only have one channel, and then the number of samples, right? So we want to append. So we want to right pad on the second axis only. And so because this is the last axis, so we just need to put like this value here and pass it in here, right? If we were to add some sort of padding to this initial axis here of the tensor, we would have needed a couple of extra values, right? So these couple of extra values, for example, would have acted or would have like provided padding for the first axis. Okay. So this is as simple as that. So let me remove all of that, but by now we have our padded signal, and so we can return it. Well, let's return the signal. Once again, here, this is like right pad if necessary. So if the signal doesn't satisfy this condition, then the signal is returned completely untouched. But if the signal has less samples than the expected samples, then of course we apply padding in here and we return the modified signal. Okay, so that's basically it for adjusting the length of the signal. And then once we have this signal adjusted, we can return it, and we are all well and good with our UrbanSoundDataset class. Okay, so now let's take a look at this in action. So let's start by seeing how this like works by like running this script and in debug mode. Okay, so I'm getting the first item in the dataset for the USD class, so the UrbanSoundDataset class. So now let me run this in debug mode and let's see. Okay, so the first item has, so let's take a look at this signal. So the tensor is as expected, the first dimension of it is equal to 1 because it's mono, and then it has 7,002 samples. Okay, so this basically means that this value is less than the 22,050 samples that we expect. So what happens is that the signal is not going to be cut, right? But now the signal is going to be right padded because it satisfies the condition for being right padded. And now let's take a look at the signal. So once we apply, so once I step through, yeah, you'll see that the tensor is now 22,050 samples. And that's because we applied right padding to it. Okay, so this seems to be working fine. That's great. Now, let me show an instance when cut, if necessary, is actually triggered and cutting is applied. So I already know that if I retrieve the first item in the dataset, that is going to happen. So I'm going to just debug this, and we'll stop here. So as you can see, the signal right now for this audio sample has 88,200 samples. So this is more than the 22,050 samples that we expect. So cut is going to be triggered. So let me step through this line of code. And as you can see, we truncated the tensor, and now we only have 22,050 samples for it. Okay, so that's great. This is working fine. What this entails is that at the end of the day, we're going to have all of our data that has a consistent number of samples, either by truncating it or by adding extra elements with right padding. That's great. Okay, so we are done with this video, but not with this class yet. So I know you may be thinking, okay, but this is endless. So we've been on this class for a very long time. Yeah, and that's true, but that's because there's a lot of stuff to do. Now, what we're going to do in the next video is quite cool, because we're not really going to do anything to our pre-processing as such, because the whole pipeline now works well. The only thing that we want to do is take this class, and rather than running it on CPU, that's what's happening right now, we want to run it on GPU. And that's the whole point of using torchaudio in association directly with Pytorch. That's gonna enable us to use a GPU acceleration directly for extracting features, applying transforms, and all of this kind of stuff to our audio data. That's great. So I hope you enjoyed this video, and if that's the case, remember to leave a like. Remember that the Sound of AI is not just a channel, but there's also the Sound of AI Slack community. If you're not part of that, you're missing on something really, really cool, with a lot of people networking and getting feedback on old stuff, AI, music, digital signal processing, and audio. So yeah, just check out the sign up link to the Sound of AI Slack community in the description box below. That's all for today. I'll see you next time. Take care.